Already thinking I'll have a bunch of questions.
But I'm going to explain it.
All
So
right.
are you gonna
Thanks
are you
everyone for joining. Happy Friday, October 25th today. I wanted to start off with Agile Austin and our mission. We want to connect people, grow professionally. We especially value the Agile values and principles and practices, and we want to figure out ways to promote that and to get more people involved in harnessing the benefits of Agile. A lot of us that have been practicing Agile for a while, we have seen a lot of benefits, and we really think that'll be great for more people to participate and more companies to participate. So we have an amazing group of folks that are on our board, and Max is on there. We have Sid, Chase, Ben, Jenny, and a lot of other people that have contributed in different ways, that continue to contribute in different ways. If you're interested in joining the group, the board, the executive committees, different SIGs, please do reach out. You can put something in the chat. We'll be happy to connect and see how you can kind of help participate, join. Hopefully you all are aware, you all go to the Agile Austin website and you kind of seen some of the opportunities of participation and education and learning and everything else.
and
There's
I'll
also a
put a
Slack
link
channel.
in
Yeah.
the chat. I'll put a link in the chat also.
Awesome. And there we go. On the left side, we also have the email website. We also have a Slack community. So if you're interested to join that, please let us know. We would not be where we are without our sponsors over the years. Many sponsors that have kind of joined us. If you want to join and be a sponsor, help the community, please reach out. Membership fee is obviously relatively low, and we try to kind of create as many opportunities of learning as possible. Please, obviously there are some benefits to it that non-members do not get. But one thing that everybody gets, especially we've kind of been pushing for that, is the Slack community access, so that there's more widespread discussions and participation. All right, so we do have meetups. There are 6 SIGs as well. Agile coaching, at scale, book club, lean Kanban, leaders, and then obviously this one, which is focused on products, AI or AI. And we're kind of open to lots of different type of topics. If you all, anyone is interested in participating, in presenting, if you have ideas, thoughts, questions, please do reach out. We would love to have more people participate and engage. I did not realize we had 7,300 members. That's awesome. Sorry. Wonderful. And I know there is also another conference coming up that Max might want to tell us a little bit about. So I'm going to open it up for him.
Thank you, Vishal. Just 10 seconds, and I'll put the link in the chat also. We have our KA 2025. That is, KA is Keep Austin Agile Conference. This is our 12th annual one. It's a tradition. It's a tradition. And it's going to be Thursday, April 24th, okay, 2025. I would love for potential speakers in the AI and product space. We would love to hear from you. So we got call out for speakers and sponsors and tickets. It's going to be a hybrid conference, so both in person and virtual. And I'll just conclude with saying it's just great for the Agile community to come together and share knowledge and love. COD 2025, folks. Check out the site.
Thank you, Max. All right. Like I mentioned, our sponsors, Platinum, Gold, Silver, and many other folks that have kind of supported us throughout the years. Agile Velocity continues to be our Platinum sponsor. They have amazing programs, coaches, trainers. ResumeX has been kind of with us for some time now as well. And we continue to look for and add more sponsors. Thank you to our sponsors. And there is something interesting that that we're starting to kind of, especially from a giving back to the community. So there's a scholarship if you want to sign up for some, some courses you want to take that allow you, that help your professional development. Definitely reach out. Again, these are granted at the discretion of the board and the community. But we are looking for opportunities and ways to give back as well. There's a link here. Let me make sure I can quickly copy it, paste it.
Yeah, and just a quick disclaimer, this is scholarships and professional opportunities that we're making available to our members. It's our way to give back to our membership community. But if people join and then in the future they have a need, want to buy a book, they want to get a certification, etc., that's what we're doing this for.
Yeah. So the link is in the chat. Oops, I clicked on the link. That's funny. All right. Agile Velocity, like we mentioned, they're offering 15% off their public workshops. So if you're interested, please do take a look. The QR code is right there. And if you're volunteering, we're always looking for great people to join our group, to join our community, see how we can and for CA, we will definitely need a lot of volunteers. So please do raise your hand. Please do reach out. We would love to have the more, the better, and it's going to be more fun then. All right, so about this particular SIG, Matt and I, Matt does all the bulk of the work, so I just kind of show up. But this has been amazing. I'm glad that we restarted it this year. We've had some great speakers so far. We continue to look for more speakers. And the great thing is that our SIG is not just Austin-based folks, but people from all over are joining. Last time we had someone from Sweden. We had a speaker from Bratislava. So we are very, very, the virtual thing, we want to take advantage of the fact that we can be virtual. Again, it's all about AI products, learning from each other on a broad range of topics with the underpinnings of Agile. All right. So upcoming, we have November 15th, we have Bunkim speaking to us about security considerations for AI. December, we typically do it the last Friday of the month. I don't think we're going to get a lot of people joining then, so we're going to skip it. And then January, we also have Elena talking about generative AI and risk management in product design. All of those should be very interesting and fun topics, lots of moving parts. And, by then, I suppose the world will have changed anyways. So it seems we're moving so fast on AI. All right. So with that, I'm going to hand it over to John. John has been a huge supporter, participant, everything. I mean, Agile Austin, he's been there for a long time. We've known him for a long time. He has great ideas. He also has some books, if you guys want to look him up. And, look forward to kind of this conversation. Obviously, it's very intriguing, the topic and the title. So without further ado, I am going to hand it over to John.
Awesome. Thank you, everybody. Let me get my screen share up and going. Just give me a moment, please. Okay.
Looks good, John.
Good. Yeah, the Mac security gave me an extra pop-up this time. I'm like, I don't know what this is. Okay, but we can see it. All right. So today's topic is on explainability in AI systems. Now, it sounds a little confusing because it kind of is a confusing topic, but I want to break it down and make it much more simple. I've got two parts to this talk. The first part is actually just really, really kind of intuitive. The second part, I dug in under the hood a little bit into an LLM, and I want to show people some stuff. You don't need to worry about the technical details. I know that this is not a coding group, this is a product group, but how this thing works and what is stored in databases really matters in terms of how we explain what AI systems tell us and what should we make of it. And with that, let me just give a little bit of background. I have been sorry, Zoom's always in the way. Okay. I've been in Agile and in development since the late 90s, which means that I earned all the gray hair that I've got. I founded Just Labs here in Austin as a consulting company. And kind of my background where I got started in AI is when I co-founded Aptage AI in 2016. And my co-founder, Murray, he's PhD in math. He was creating the algorithms, but I learned, I was mentored by him in a bunch of things. This is really where I dug into AI is 2016 is where I started into it. So these pictures, when you were a kid, did you ever learn to whistle? Or did you learn to ride a bike or swim? These things are stuff that many, not all, but many children learn one or more of these. I think the stats I've seen is about 50% of the population has learned how to whistle, something like that. Now, when you learned how to whistle, did somebody teach you or did you just have to figure it out? That's the key. That's the crux of this. I remember when I learned to whistle. I think I was about 8 years old and I couldn't whistle and I wanted to. And I tried, it didn't work, I failed. I remember that I went downstairs into the basement at the house that I was in. And I spent, I think it was about 45 minutes trying to whistle. And I finally made a noise. I was, you make all the funny noises. And then I started that and I smiled. I was so happy about it. I did it. And then I tried to do it again and I lost it. And I spent another 2 minutes trying to refine the right shape, the right form, and I figured it out again. And now since then, I have been able to whistle. That's how I learned how to whistle, is alone, because I didn't want anybody listening to me in the basement, just trying it out. And eventually I figured it out. This is learning by trial and error. And there's a lot of things that we do by trial and error. Riding a bike, people can give you advice on how to ride a bike, but eventually you have to learn the feel of it for yourself. And swimming, there's mechanics that you can try and practice, but before you really learn it, it's something that you have to figure out for yourself. So these are all things that many people have experienced at least one of these, but this style of how you learn, it's not teaching, it's learning by trial and error. And that's one of the key things that I want to highlight. And what I want to do then is connect this up with neural networks. Neural networks are a very important and very popular kind of AI system. They also learn by example, which is a kind of learning by trial and error. So neural networks, you can feed in a bunch of pictures of cats and these boxes and squares and circles. As you're training these neural networks, they figure out how to put all the right numbers in all the right boxes and get the right answer on the output. Is this a cat or is this not a cat? And neural networks learn by example, which is a kind of trial and error. And so neural networks can't be taught what is a cat, but they have to somehow figure out what all the right numbers, the weights, the properties, and all the other various things in here are to create a good output, which is, yes, this is a cat, yes, this is a cat, no, that's not a cat, and this is a cat. And so neural networks fundamentally learn by example. And this means that they're also, you can't teach them how to do it. They can't teach anybody else how to do what they do. And they're not explainable. That's the point. That's the very simple point that I want to make in this is neural networks are really powerful, but they're not explainable. And one of the reasons that people get confused is because a lot of things talk about how to explain AI or how to interpret the results of AI. Fundamentally, though, the basic approach for how neural networks work is not an explainable technology set. And what I mean by that is that even the data scientists that build these systems can't explain why they give an answer. Why did this cat get picked as a cat, but this other cat was flagged as not a cat? It was an error in the output. Nobody can explain that. And so that's the fundamental thing, is that some AI systems are like learning to whistle, and they're not explainable. And so that was the biggest takeaway that I wanted to provide here. But I think that there's definitely more that we can say there. Some definitions, just to kind of set the stage. Explainability. When I say explaining explainability, I mean explaining how we came to a conclusion or an answer. And this is important in a lot of aspects of our life. But it's also true, though, that not everything humans know can be explained. There's a tacit knowledge, we know more than we can tell, is very true. And humans can't explain how they learned how to whistle either. So it's not that it's machines are bad at this and humans are good at this. It's some types of learning can't be explained, is really the takeaway. The fancy word that AI systems use is interpretability. And interpretability means, can we explain how the AI got the answers that it got? And so explainability and interpretability are pretty much the same thing. Now, I put up here as well another definition, which is useful. And my point is that, well, being able to whistle has some use and value, but AI systems that are not explainable can still be very useful. And that doesn't mean that they can be used for every purpose, but they can be useful in many ways. And setting the bar that they must be fully explainable will take away a lot of very useful things that just cannot be explainable. So that's something that I want to make sure that we've got a kind of a sense of. If we want to contrast learning by example with learning from a model, then there's another way that we learn things. On the left is a recipe for zucchini bread. It's my mom's recipe for zucchini bread. I'm sharing it with the world right now. This is a recipe. It is essentially, it's teachable. Like how to mix things might be a little bit of a self-learned kind of trial and error, but fundamentally this recipe it has instructions, it's got a process. And the other example that I put on the slide is a knife skills class, how to hold a knife and how to hold your fingers so they're curved over so you protect them from getting cut. This is another teachable skill. There are experts that have figured out ways that things go well. They can write them down, they can teach them to other people. And so these are learning from a model, either following instructions or getting the rules for something like curve your fingers and hold the knife with your thumb and index finger together. Those rules are definable and can be shared with people. Hang on a second. And so learning from a model is another way of teaching and learning. And the great thing about the model-driven learning processes, they're very explainable. They have explainability built in because you're teaching the why, the how, and the what to do when aspects of things. This is an example of a different AI system. This is a Bayesian network, which is an expert derived model that in this case is talking about online sales and the probability. Changing product location, changing promotions, and changing price all have probabilistic effects on the sales and the likelihood of sales of a product. This is an example from an academic paper that was using a Bayesian network to predict when sales will go up or down, or how to optimize sales. Where do we get the most value for the most bang for our buck and the most choices? Now, this model was derived, and these probabilities, the catalog 47%, in-store 8%, all these probabilities were learned from experts and from some of the data out in the real world and looking at things and testing some things. And then they put together this model to make some predictive effects for how are you going to optimize sales. This Bayesian network model is different than a neural network. This Bayesian network is very, very explainable. And you can interpret exactly where all of these percentages came from, and you can use it to test the experts' intuitions of how the system is going to play out. And so what these types of AI solutions enable you to do is to have expert-taught systems that are still AI systems that still have probabilities and calculate and predict outcomes, but with a very different mechanism. Now, Bayesian networks are not used for many things like for identifying cats or for the underpinnings of LLMs, because they're not those types of networks tend to be very, very big. And so Bayesian networks work well in slightly smaller scales and smaller scopes of a number of variables in a problem, but they're very explainable and they work to augment the expert opinion of how to do things. So if I talk about these neural networks and LLMs that are built on top of neural networks, including ChatGPT, by their nature are not explainable. They're just not. Why we got the answer, why the LLM wrote these words, there's no explanation. Nobody at OpenAI or Meta knows how to explain exactly which words were picked there. And this actually, earlier this year, at an AI conference, Sam Altman, the CEO of OpenAI behind ChatGPT, is quoted as saying, "We certainly have not solved interpretability." And then the rest of the notes from the conference go on. Basically, he was dodging the question of how do you explain the answers and the outputs that ChatGPT gives. If the reality is even the data scientists at behind ChatGPT don't know how these systems give the answers that they give. And that doesn't mean that they're not useful. It just means that if we need to have a system that is fully explainable, then these technologies put that at risk. And what are some examples of domains where the decisions require high degrees of explainability? Medical decisions often require a lot of explanation and kind of root cause analysis to figure out why you're doing something. Many financial decisions with money on the line, you don't want hallucinations to be where you invest your money. And there are many military applications as well that require, sitting in front of Congress and explaining why things work the way that they work. So there are many domains that require high degrees of explainability. And in those cases, the ability to use a chat LLM and a neural network really underpins or really undermines the ability for us to explain how we came to the answers that we came to. All right, that was all. I'm going to pause there. I'm going to go back up to here. Before I move on to the second half of the talk, I just want to pause for a minute and just give people a chance to ask questions about that explainability topic, how neural networks are like whistling versus a recipe. Does anybody have any questions? I haven't.
As people maybe think about a question or two, John, it's very interesting to hear it in this way, because as what minimal interaction I've had with like in any kind of an AI platform, it's very much a trial and error. And I think it's so new in so many ways that it's gonna take a while and a lot of practice for it to actually start to add real value at an enterprise kind of like a level. But there are breakthroughs already. They're breakthroughs, and that's why there's a lot of hype. That's why there's a lot of hype, because there are breakthroughs already. But from what I've seen in the enterprise space, I've not seen a breakthrough myself. I mean, directly, right?
Yeah. So there's two areas where they can have a breakthrough. They can have a breakthrough in how useful is it, how valuable is it. And you're right, there's very mixed bag of results right now. There are lots of things that look really promising, but when you really try and use them, they don't have as much oomph behind them. Absolutely true. And there also is research into the explainability, the interpretability of these systems. That research also has not had a big breakthrough. There's a lot of talk, and actually that's part of my second half of this topic is, no, it's a great segue. I'm glad that you asked. The research that's going into the explainability, there's lots of hope, but there's not a lot of answers yet. And so fundamentally, the point that I wanted to get across is these kinds of neural network systems are fundamentally learning by example and fundamentally not explainable. And unless there's some radical breakthrough in research, that's not going to change. All right, Any questions before I move in? Okay. All right.
John, I had a very quick question. Sorry. I had a very quick question. So why is it like, you kind of talked about how they kind of reached there, but is it just the sheer amount of data that is being processed by the neural networks in quick time, which makes it difficult to kind of walk backwards to say, how did you get to this answer or decision?
It's both. Some of it is the sheer amount of data, the number of properties. So on this picture, there's a bunch of red squares, and then there's some purple squares, and some more red squares, and some more purple squares, and then some of the yellow dots that's kind of synthesized this out. The number of squares is like the size of the neural network. And so part of that is a sheer size. When we're the next section on this, I'm going to be using the Llama 2 7 billion parameter LLM chat engine for the example. 7 billion parameters is a lot. That's definitely too big for any human to be able to reason through in any useful way.
Right.
And so, yes, the answer to your question is that's a part of it. The other part of it is the way that this training works is as you feed cat picture after cat picture after cat picture into this pipeline of things, what the engine does for training is it tries different ways of adjusting the numbers in each of these squares. Think of like a spreadsheet with 7 billion rows and hundreds of things across, right? All of those numbers get sifted and sorted in different ways based on the next training image to see how do we optimize given where we are, how do we optimize getting a yes, this is a cat versus not cat output. And so those numbers get sifted, and the training itself just changes things based on what kind of works. And that also is not explainable. So it's both the volume and the approach. And when I was telling the story that I learned how to whistle, the first time I made the whistle sound and I smiled, I lost it. And I had to relearn it, but it took me much less time. It was real quick to learn it the second time, like another minute later. That process of adjusting and tweaking things is similar to how neural networks get trained. And there's no explaining that.
Okay.
I see a hand up for Roger.
Yeah, I put it in the chat, but I guess there's sort of a distinction here between explaining what's happening on the inside of this box. If you treat the model as a black box, there's explaining what's happening on the inside, but then there's also a form of explanation where you are just saying, if I change the inputs, I can sort of explain how that affects the outputs. And there actually is a library for that, and sort of a whole concept for that called Shapley or Shapely, and I put a link to it in the chat. So you can with a neural network or any sort of other sort of very complex model achieve some level of explanation, even if you can't sort of explain the inside of that black box.
And that's great. Thank you for sharing that first. Second, I do have a clarifying question that you might have a clue on. Does that library, the Shapely work, does that provide explainability or does that provide repeatability? Like if we put in the same similar inputs, we understand how they change into outputs, like repeatable outputs, or is it one or the other? Roger raised his hand again. He's muted. Can somebody ask to unmute? I think I found the button.
Let me see if I can find
it. He can. Roger, you can unmute. There you go.
Okay, thank you. Sorry about that. What it's doing is it's telling you basically, if you change these levers, these inputs, if you change, let's say you have age, gender, a variety of inputs into making your prediction, the model making its predictions, it can tell you which of those variables are the most important when they change. So
Cool.
It's not just sort of repeatability. It's telling you like, oh, you know what? If you change the age in the input, doesn't make any difference. The model will always generate the same predictions no matter what age is input into the model. That would be an example. And so it sort of quantifies the importance of each variable. And it will also sort of, if there's a directionality to the prediction, like it's just a probability of, it can also tell you, as a general rule, this variable, higher values of this variable will lead to higher probabilities.
More means more versus more means less.
Yeah.
Cool. Okay. Well, I'll definitely take a look at it. And like I said, I hope that we find some really important breakthroughs to be able to make these things more explainable, which would be really good. They can be useful on their own, but explainability is not today a done thing. Let me go down to this one. So here's where I got into the second one. A few months ago, I was at a different meetup, and there was a big vendor, like a big consulting vendor, claiming, this is the second bullet point, a big consultancy claiming that vector databases made the Gen AI solutions explainable. And I didn't argue in the thing, but I scratched my head and I was like, okay, quite get that. And I've seen other Gen AI vendors claiming unprecedented levels of interpretability. And I'm like, well, okay, show me how. And I can't find any details. So all of this was alarming to me because I think that the marketing messages are getting spun, or the people that are sort of technical in the space, but maybe not all the way down, are hoping that there's answers for this problem, and I don't believe that there are good ones yet. And Roger, I hope that the Shapely stuff has some good use, but this was alarming to me enough that I decided to write some code to visualize the data. And my goal is to help everybody here take all of these claims with a grain of salt, or a lot of salt, as the thing would be. And so a couple more definitions. Repeatability is repeating something gives us the same answer. It doesn't change. The same inputs give us the same outputs. And then random is done in a way that is chosen by chance, like rolling dice or something like that. And then the other definition, temperature, is what what ChatGPT and Gen AI systems call the amount of randomness that they use. And ChatGPT and other Gen AI LLM solutions actually introduce a random poll on the words that they're writing next. They don't pick the word that's the most highest probability every time. They pick randomly from the top probable words every time. And that's an interesting thing. I've figured out a good way here in Austin, for anybody that's in Texas, to understand this. This was the TripAdvisor top 10 barbecue joints in Austin list. And we don't have time to argue about which one should be at the top of the list or second or third. We're not going to get in the argument. This is the TripAdvisor one. We're just going to take it as it is. But the way that the LLMs, that ChatGPT works, is it says, well, we're going to take a random choice from the top of the list as the next word, what we generate. And this is why when you ask ChatGPT the same question twice, it gives you different answers, because it keeps on randomly picking different words and going off in a slightly different direction every time. And so the temperature in an LLM is the randomness that they're picking from. So they introduce randomness, which is fine. Randomness does mean that, part of explaining things is a little harder, but randomness is not bad. Monte Carlo simulations and all kinds of things are for it. But this is important to know why ChatGPT gives you different answers. What I did to understand this claim that vector databases provide explainability is I traced a couple of things that, and this is going to get a little bit deep, but we'll have pretty pictures to look at too, so it'll be fine. Embeddings is kind of like the LLM's mental model of what you've just given it. And it's like the If you feed in a document or a question into an LLM, it has a perspective, it has a data model of what that looks like. You can take that rich embeddings model and compress it and take all the embeddings and get the average for each one of them. And that becomes then a list of data that is a vector. And a vector is much smaller than the entire embeddings model. And then the vectors can be compared for similarity. They're closer together or further away from each other. Now that's a whole bunch of terms, and what it means though is if you're using a vector database to do similarity between different things, the LLM is understanding what you told. I'll air quote understanding what you told it, turning it into a data structure that gets turned into a vector, and then you can do similarity detection on the vectors. And if a user is searching for something in a vector database, really the matches are the result list. So if you're asking an LLM to give you some answers, it gives you like the top few things. Those are the most similar things to what you're looking for. And the top result, the first result, is really important because humans generally bias towards the default or the most popular option as a psychology principle in the psychology of nudge. Okay, that was a ton of definitions. I don't want to bore everybody with all this. Let's look at an embedding. So what I did is I used the Llama 2 7 billion parameter LLM. This is a free, it's from Meta, it's an open source LLM. You can get this. And what I did is I gave it a sentence, lorem ipsum dolor. I gave it this sentence at the top as the input. And I asked Llama 2 to create an embedding for it. This embedding that it produced is 4,096 items long, and each of those items, that's this way. So here's the 4,000 axis is this way. And each of those has 41 pieces of data, numbers like 0.50723 and negative 2.87 and all these things. And so there's 41 numbers across, and there's 4,096 of these things. So this sentence, the LLM created an embedding set of data for this sentence that has 167,936 data points. That's quite a lot of data, and it looks interesting. It's pretty cool. This is the mental model that this LLM had for that sentence. Now, what do we do to turn it into a vector? The vector then takes these 41 data points at this row, and the 41 at this one, and the 41 at this one, 41s, and it averages them. This is actually the code. It uses the mean function. The mean is the average function. And so what we end up with is just a list of 4,096 numbers. And so we took all of that information and squished it down into 4,096 numbers. Those 4,096 numbers, that's small enough that you can put in a database. And that's the vector that would go into a vector database. Now, here's the question that I would answer. Obviously, this is really high up here. This is maybe the highest or the second highest. This is perhaps the lowest number here and another low number here. How did the LLM decide that these were the types of data values for this sentence? Now, that's a question we don't really know the answer to. And there's so much information here, I didn't know what to do with it myself. So I decided to simplify the input down, and I gave it blue as the input, and I gave it green as the input. And so we got these are two embeddings. The input is only the word blue, and the input is only the word green. And the embedding, the data that the Llama 2 LLM created now has two data values by 4,096 rows. So it's much simpler. The input's much simpler, the output's much simpler. Now, if you look at these, I'm just going to pause for a moment, stare at these two a little bit. There's a lot of similarities between them. And then if I look for areas where they're different, really this top right has differences that are interesting, but a lot of the rest of it has got a lot of similarity. So this one here, this big green wedge goes way up, and then there's a bunch that are down. This one doesn't have the big green wedge. So much of this is similar, and then there's some important differences between these two, which, I mean, of course, this makes sense. The blue and green are not the same. They're going to have different representations and different data. If I do it for blue and red, okay. If I do it for blue and red, well, we still see there's some things that look sort of similar, but this one looks a little bit more visually, this one looks more different. But these are the embeddings for blue and green and red. And now a little bit more technical. We don't need to get too bogged down in this. What do we do with vectors? So a vector database is used, we can put our company FAQ documents or RFQ documents into a vector database and do stuff with it. Well, vectors are directions. If you think about GPS coordinates, I'm in Austin, Texas. Many of us might be in Austin, Texas. Some of us are around the world, the country. With two coordinates, two GPS coordinates, I can identify where I am on the surface of the Earth. And then if somebody else is someplace else, they've got two more GPS coordinates, and I can say, I want to go up and over to get to them. And the up and over is two directions. Those are two vectors. Moving up, moving over are two vectors, and they can give us a place to be. And then we can ask, given those vectors, the directions of how to get from here to there, we can ask how far apart are they as well. And so think of this vectors as having like coordinates to get somewhere. And then you can say, well, is this place and this place really close together or not that close together? So it's a long-winded way of saying, of course, there's 4,096 of them. On the surface of the Earth, we just have two GPS coordinates, but in vector databases, it's a lot more. But the Euclidean distance is the way to do this as a common way of doing vector similarity. So I wrote some code, I did some Euclidean distance between these things, and blue is closer to green than anything else, than the other two. And blue is the furthest away from red in this case. Now, why? How do we interpret this? Why is blue and green closer to each other? Well, I don't know. Perhaps the training data set had more blue and green in sentences and paragraphs together. Perhaps the concepts got tied early in the training set and they were stronger. I don't, it just is, clearly it is, but I don't know how to explain why. I've got some theories, I've got some ideas. But then if I try something else, the other common way, the second most common way of doing similarity detection between things is cosine similarity, which means are they pointing in the same direction or are they pointing away from each other? Okay, this is just another way of doing similarity that's also commonly used. If I do similarity detection with cosine similarity, I get the opposite answers. And so how do I interpret this? Why is this true? The blue is now closest to red and furthest away from green. Well, that doesn't make any sense to me. I don't know how to explain that or interpret that. And remember, this has 7 billion parameters that these words are fed through to generate those embeddings to create these results. So there's no way that I can just look at the database and scratch my head and figure it out either. And so this is some of the under the hood, what's going on in terms of the vector databases. They're very repeatable, but I don't believe that they're explainable in the way that some of these organizations hope that they are. Now, I did one more test just to see something. The model that I was using was the Llama 2 7B-HF. And there's another one, the Llama 2 7B-Chat, which is optimized for dialogue use cases. So what the meta engineers, data scientists did was take the first one, train it further with more dialogue conversational work and parameter tuning, and then release that one. And so they took the first one, did more stuff, and said it's a new variation of it. Now, in this case, if I run the same test with the Llama 2 7B chat variation, I get a different order as well. I get blue, the closest together is still blue and green. Those are the closest together in this case with Euclidean similarity. But now the red changed closeness with the blue and the green. And so if I show you the original one, here's the first test. So red and green are closer. If we read it backwards from the right, red is closer to green, red is further away from blue. It's a bigger, further distance away. In the chat variation, red is closer to blue and red is further away from green. I can't explain that. I have no idea why. And there's 7 billion printers, and this is a small one. This is the kind of LLM that can run on my laptop. And the big ones are big. And so I don't know why this would be true. I have no way of figuring out how to get under the hood to even begin to assess why this would be true or how this might happen. And this is the simplest example, red, blue, and green, that I could come up with. So this is what I wanted to just kind of show people and say, even though the vector databases are repeatable and they give us like a number, an answer, that doesn't mean we can explain why it picked, the LLM picked an embedding that was vectorized, that was closer to something, that we can explain that. That's the point that I was making. So take any claims of Gen AI or LLM explainability with a grain of salt, because this is a look under the hood at some of the data and code. The next, and I'm almost done, we're right near the end. So what to do from here? If we need things that are useful, but not necessarily explainable, then neural networks, LLMs, and deep machine learning techniques can be very, very effective in some cases, not in every case, as Max and I both have experienced. But in many cases, they can be very useful at doing things. If you need explainability and you need to be able to explain how a model generated this answer, why did it prescribe this medicine, why did it recommend this course of action, then model-driven approaches, expert-driven approaches, Bayesian networks, causal networks, the original AI technologies are much more explainable than the very, very big neural networks that are being used today. They can do amazing stuff, but they're not explainable, is the big point that I want to make. These two books are very good treatments of some of the math of explainable systems and how to do probabilities and predictions well. Both of these books are written by academics who are a little bit bitter around some of the last 100 years of math controversies. And there has been a fight between frequencists and Bayesians for a long time. But if you can get past that kind of the kind of upsetness of some of the history around this, both of these books talk really, really interesting math about how to interpret and predict things. With that, that's about it. Any questions? Or does anybody have any answers? Anybody know why red is closer to blue now?
Yeah, Matt, do you know?
Me? Oh, yeah, because it was trained on a lot of police lights. And the first one was trained on Christmas lights.
There was a comment from Roger again. Predictability random is a pretty cool variation on the classic book Predictability Irrational.
Cool. Predictably irrational?
Yes.
I'm gonna try to just turn off the allow all participants to they can
For the
start,
last few minutes.
yeah. They can start video. I don't know if that means they can, unmute themselves. There we go. There. Now everybody should be able to start video and unmute yourself, because if you stayed this long, you're probably not a Zoom bomber.
Well, come on in, fully join the meeting.
Yeah, but the video's already started, but
Hey, John, the couple of questions. Can you go back to the Bayesian analysis bit? Yeah, that one.
Yep.
So we're pretty familiar with tools such as ChatGPT, Anthropic, Perplexity, all these kinds of things that are hitting the mind equals blown every day. The 10,000 things that just rocked and changed our world. As far as tooling around expert systems, is there kind of a like what is there an analog? I mean, I know there's lots of like systems that analyze data and use general algorithms to come up with answers and things like that. But I don't know, like, is there sort of like a similar, here's the tool that you use that's more of a Bayesian model?
There are at least several Python libraries that can implement Bayesian models, Pomegranate, Stan. I know that there's at least one Java library. It's a commercial tool for visually building these from Fenton and Neal, Risk Management and Analysis Using Bayesian Networks is their book. I forget their tool name. Agena Risk is the kind of graphical tool that they have. It's a Java-based system, commercial license. The Python libraries are open source. There are these models have not made their way into the common AWS analysis and Google analysis servers. They're not part of the stuff that's out there generally. In terms of where these are being used more and more often, they are being used in many ways in many different environments, but less. It's less loud than some of the other kinds of things. What is the? I don't want to make it up on the fly. There's a no, I'm not going to remember it. Not off the top of my head. One of the things, and actually the book on Bernoulli's fallacy, the book on the bottom, this one talks about the crisis of modern science. If anybody's heard of the reproducibility crisis, it's not about neural networks, but the p-values, the p05, p.05 value for publishable criteria that has been used for not 100, like 50 years or something. That is actually coming into some question. And this book in particular by Clayton suggests using Bayesian probabilities for all scientific publishing and decisions, because what people are finding in the last couple of decades, literally the past decade or two, is the reproducibility crisis, which is people have started going back and trying to reproduce core foundation science, sociology, medicine, just core science that we have that many other things have been built on. And what they're finding is that a bunch of them, maybe 30% of them, are not reproducible. That they worked once and they got published and everybody uses them, but they're not really true. And that's the ability to use different techniques, Bayesian techniques, is what this book is about.
Is one of the I don't know if you, maybe hopefully I didn't miss it, but I mean, there's clearly some sort of drawback with going with a Bayesian network or, sort of these causal networks.
Yeah.
Otherwise, we'd be using them and we'd be able to very quickly explain things.
Yep, scale and compute power would be kind of at the top of my tongue there. Trying to build a Bayesian network that is big enough to identify cats and not cats that would be a huge Bayesian network, and the compute power for that would be ginormous. And so what the neural networks have an advantage is that they can just find things that work, and then they work and they're optimized and you can use them. The Bayesian networks and the causal networks use underlying kind of like root level, foundational level probability math and inversion and matrices and all the kind of coding that does that. They end up being a lot more compute intensive and taking more time. And so I can't think of any examples where Bayesian or causal networks would work for a ChatGPT like system because it's too big.